Hey there, remember the associative law from grade school? When you write down the product of, let's say, some set of numbers, some number of numbers, let's say A times B times C times D, um, you actually haven't specified in what order you should do the multiplications in. It turns out we're lucky because multiplication is associative and it's also commutative, so you can actually do it in any order you want. But let's say that I had to actually specify. Let's say I was like trying to write a multiplication for a computer, and I had to specify where the parentheses go, what was the order of operations. And let's say I just wanted to keep them in the same order. I'll explain why I need that in a moment. There's 5 ways you can add parentheses to this expression to get multiplication in pairs, right? You can first do A times B, then multiply by C, and then multiply by D, or you can do A times B times C, and then multiply that by D, and so on and so forth. There's several different ways you could do this multiplication. And of course, on the computer, on a computer, we multiply pairs of numbers, so we would have to specify some particular order. It doesn't really matter in this case what order we decide to choose because it's going to be the same computation. We're going to have to, in the end, do 4 multiplications, or I guess in this case, sorry, 3 multiplications to get the final output. But that's actually not true when it comes to matrices. So let's talk about what happens when you're multiplying matrices. So there's a fact I learned from grad school, and I remember this being something of a eureka moment. It's very common to imagine a situation where you have a bunch of n by n matrices, let's say A1 through AK. These are n by n matrices, and you have some n-dimensional vector V. Now, I assumed at first that it doesn't really matter in what order you multiply these things together, right? I was thinking, why not just multiply all these matrices together first and then multiply that by the vector? And it turns out that that's actually not the fastest way to do it. Let's for now just assume you're using the naive algorithm for matrix multiplication. The naive algorithm is the one where you simply just compute every entry in the final matrix as a dot product of the associated row and column of the 2 matrices being multiplied together. We showed actually in an earlier lecture that there's a better way to do this. You can actually get something that's faster than O of n cubed, but for now just assume that we're using the typical standard O of n cubed algorithm for multiplying 2 n by n matrices. So if you decide to go with approach 1, where first you just multiply A1 times A2, and then you multiply that by A3, and you multiply that by A4, and so on and so forth, you end up multiplying the first k matrices together, and then you do the vector product at the end. The alternative is you take AK times V, right? That's a matrix vector multiplication. And then you take AK minus 1 times that, which is again a matrix vector multiplication, and so on and so forth. Those are the 2 methods you could use. So let's just be precise about the running times of the various ways we could do this multiplication. You'll notice that this first multiplication here, this takes on the order of n cubed, right? And then once you get that, you have to multiply that quantity by A3. So this takes on the order of n cubed, right? And then so on and so forth. Every time you do a matrix multiplication, it takes on the order of n cubed. So we'll say dot, 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 dot. And then in the end, you'll have this whole thing right here, which is a big n by n matrix, and you're going to multiply it by this vector. That final operation, an n by n matrix times a 1 by n or an n by 1 vector, that takes on the order of n squared. A matrix vector multiplication takes on the order of n squared. So in the end, you end up getting O of n squared. But in total, right, you had to do k matrix or k minus 1 matrix multiplications first. So you end up getting like k minus 1 times n cubed plus, this is on the order of, plus on the order of n squared. In total, this is all on the order of k times n cubed, right? Now let's consider the alternative way. Let's say approach 2. If we decided to do approach 2, you'll notice that every multiplication in approach 2 is a matrix times vector multiplication. So here, this is an O of n squared operation, because it's a matrix times a vector. The next one's going to be another O of n squared operation. And if we keep going, we're going to get an O of n squared operation for each one of these things. If we do the last one's again going to be an O of n squared operation because AK times V is a vector. So every time you multiply a matrix times a vector, you get a vector back. So every one of these operations is a matrix vector operation, and in the end, the running time is going to be on the order of k times n squared. That's faster than k times n cubed. So we actually got a better algorithm by doing the multiplications in a smarter order. So then we have this question, given any sequence of matrices that we want to multiply together, what's the best way to do that? That's the problem of chain matrix multiplication. Let's get to that now. All right, so the general problem goes as follows. You're given these k matrices, A1 up to 8k, and let's say that the sizes of the matrices is m sub I minus 1 times m sub I. Now, you'll notice that to make sure that we can actually do this multiplication, we have to be sure that the dimensions match up appropriately. That's why we're assuming that the matrix I has dimension mi minus 1 times mi, so that matrix A sub I plus 1 has dimensions m sub I times m sub I plus 1. That ensures that, the dimensions are matched up so we can actually do this multiplication appropriately. Okay, so what's the minimum cost now for computing A1 times A2 times all the way up to AK? What's the cheapest way we can solve that problem? So let's just even forget the actual matrices. All we need to know is the dimensions. The dimensions are the important part here. And again, let's just remember that we have to decide, how do we break this multiplication up into some binary tree? You can consider here we have, let's say, 4 matrices we can multiply together. We could solve them in this, we could multiply them in this order using sort of this binary tree representation. Right, first multiply A times B, and then get the product of that, multiply that times C, and then get the product of that, and then multiply the whole thing times D. Or we can multiply A and B together, and also separately multiply C and D together, and then take A times B and multiply that by C times D, and again, then we would get the final product. Both of them give the same result, but we want to know what's the best order to do these operations in. All right, so I'm just going to give you the solution, on the dynamic programming solution for this problem. It's a very neat solution, and it's quite cute because it's very simple, and it should feel very similar to the types of things we've done so far. What we're going to do, the subproblem we're going to try to solve is this Cij subproblem. So Cij is the lowest cost for computing the product ai times ... all the way up to aj. So it's the lowest cost for computing this segment of product of the matrices from I to j. So we're going to try to solve this subproblem Cij, and then we're going to try to figure out how to do this in a recursive fashion, how to find a good recurrence for this thing. So to compute C of I comma j, the trick is, the thing we have to consider is, where are we going to break this sequence from I to j into 2 pieces? Remember, at some point, to multiply all these matrices ai up to aj together, to do that, we're going to have to somehow find a segment where we first multiply the first segment of matrices together, separately multiply the second segment of matrices together, and then combine the products by multiplying the 2 resulting matrices we got. And the only question is, where do we make that split? We have to decide, where do we split the sequence up so we find the optimal way we will recurse by finding the optimal way to multiply these first I to D matrices together, and then the D plus 1 to J matrices together. We're going to recurse by finding the optimal way to multiply those matrices, plus the cost of multiplying these 2 resulting matrices we got from these recursive calls, right? But the only question is, where do we make this split? D. We have to decide where we choose the dividing point between segment 1 and segment 2. And what we're going to do is we're going to consider all possible solutions. So we're going to minimize over D here. We're going to choose the best solution over D. So in this case, the recurrence is relatively straightforward, right? What we're saying here is that we want to find, to solve the Cij subproblem, we first have to pick a segment D, which is where we're going to split the problem up into. We're going to find a way to multiply the first I through D matrices. We're going to also optimally multiply the D plus 1 through J matrices together. We're going to get 2 matrices, and the 2 matrices we're going to get are going to be of size m sub I minus 1 times m sub D. We're going to get another matrix that's of size m sub D times m sub j, right? That's going to come from this recursive call and this recursive call. Now when I want to multiply 2 matrices that have size m sub I minus 1 times m sub d and m sub d times m sub j, what's the cost of that matrix multiplication? Now I want to multiply these 2 resulting matrices. Well, this is the cost of that matrix multiplication. m sub I minus 1 times m sub d times m sub j. I guess I didn't specify exactly why that's the case, but if you just go through and think about the naive matrix multiplication algorithm, you're going to get that expression as the running time for computing the resulting matrix, right? Because every time you want to fill in an entry in the final matrix, you're going to have to do an m sub d sized dot product, and the resulting matrix is going to have size m sub I minus 1 times m sub j. So you end up getting a running time of m sub I minus 1 times m sub d times m sub j. So this is, again, the cost of this right here. Oh, this is the cost of the final matrix multiplication plus the cost of solving the two subproblems. So this is basically our recurrence. The only thing I need to specify is the base cases, and the base cases are easy. When the segment is just goes from I to I, when you only have one matrix, there's no cost for matrix multiplication. You have a segment with only a single matrix, you can assume that costs 0 time to do any multiplication because you have no multiplication to do. And this is basically it. This is basically the recurrence, and we're essentially done here. There's only one small issue, which I'll mention when we show you the pseudocode. All right, so here is my Pi pseudocode for solving this problem. I did actually run this, and I checked to make sure it works. Let's just take note of what this algorithm is doing. First, it's initializing an array. This is the initialization. Some array of size k by k, which is just going to store the subproblems. It then does the base cases, which is right here, right? It fills in the base cases, the I comma I base cases, like we said. And the only other interesting part about this, this should look very similar to what we just showed you last time. The only thing that's a little bit interesting here is the order in which I actually solved these subproblems. It's not obvious, but to make sure that when you try to do a recursion, you have to make sure that when you compute Cij here, that's referring to two subproblems that you've already solved. And these two subproblems that you've already solved, which is going to be C of I comma D and C of D comma 1 comma J, you have to make sure that those entries in the matrix are filled in. And what this requires is that basically you're going to start with this table, which is k by k, right? You fill in diagonal first. So you get the diagonal, put in zeros along the diagonal. Okay, we don't even care about this part. We're not even going to look at the lower triangular part. We don't care about. But we have to fill in the matrix now in this order. First, we do this one first, and then this one second, and then so on. Where we have to go along these diagonals. So my code here had to specify first what the delta is, what the offset was. The delta just means how far off from the diagonal are we going to be filling in, and then we go from from 0 to k minus delta, and j is just I plus delta. J is just what I is plus the offset, and the offset again is just this value delta. The only other interesting part here is just I'm using a Python list comprehension to compute the minimum over all values of D. But again, this is following exactly the same recurrence that I showed you on the previous page. This last line here is simply computing the minimum value over all possible splits of the sequence of matrices I can write inside to split them at some D, and this just minimizes over all the D. Finally, the return value is C of 0 comma k minus 1. I filled in the whole table. Now what I want to do is just, I just basically output. The output is going to be this entry right here. That's going to be the entry of interest for me, which is going to tell me, what's the cheapest way to compute the product of the first to kth matrices, right? I'm going to multiply them all together. Now, what's the cheapest way to do that computation? So this is it. We've solved this problem. Maybe only one more thing I'll address is what's the running time of this algorithm. Once you see this pseudocode, it's pretty easy to figure out what the running time is. Right? We have let's say we have an O of k squared operation here. Right? We have O of k squared for, let's just initializing some k by k array. We have an O of k operation here. We have an O of k operation here. I can be as large as k, delta might be 0, so I can be as large as, I guess k minus 1. So we have another O of k operation here. And notice that this last minimization term, this last minimization is another O of k operation. So we actually have these like three nested, we have some nested loops here, which are all in the order of k. So this whole thing is going to be, this whole sequence of loops right here is going to be on the order of k cubed, right? Because of the fact that we have these nested loops, three nested loops that are each in the order of k. So in the end, our running time is going to be on the order of k cubed. And that's cool. That's nice, and it's a reason. It's a polynomial runtime, so we're pretty happy with that. Cool. So today actually is my last recorded video lecture for this course. I have to say I really enjoyed making these videos, and hopefully they were educational and occasionally fun to watch. It's been a new experience for me, and I'm of course still learning. But working on my YouTube skills has been one of my educational activities this semester, and I'm glad I had the chance to practice on you guys. Let me go out with just a couple of more entertaining moments and to remind ourselves how this half of the semester went. I'll just mention that the word of the day is fox. The word of the day is fox. And it's been great. And of course, I'll be around for the rest of the semester. Feel free to give me a poke if you guys want to chat about anything. But this has been a lot of fun. Thanks, guys. Look how cute this dog is. Hey there. Don't forget to smash that like button. He thinks French accents are silly. You know, I want to tell you just one more thing. It so happens that I have a secret for you. Professor Crepe is actually the same person as Professor Abernathy. It was me the whole time, guys. It was me the whole time. Fooled ya! Fooled you! Woo!